Right. So, hello, my name's Ivan Scattergood. I'm the CTO at TDAB. And TDAB's mission is to radically accelerate the building of industrial IoT-powered businesses through decentralized AI. Now, it's quite a mouthful, so I'm going to explain the opportunity and why we're doing it, and a project that we've been working on using it. And so there is a massive customer opportunity in predicting and diagnosing machine health using AI. Now, we're trying to predict the failures to maximize uptime and yield. Basically, we're trying to minimize wastage on production lines. And this has an estimated value for manufacturers over $500 billion. Now, one of the problems that we have is that a lot of the companies are having problems getting their projects past the POC phase, which I'm sure you're all very aware of. And our biggest opportunity is in that mighty middle. So I'm going to explain a case study that we've been working for the last 18 months with a customer on, and I'm going to explain the problem and the solution. So basically what their problem is, they're trying to make cans, and when they're trying to make cans, they're making cans out of a sheet of metal, cutting it into cups, and then putting it through quite a torturous process to extrude out into a metal can. And if something fails in that process, if the can tears off, they have a spoilage event, and that causes their manufacturing process to stop. Now, thing is, if we can reduce that by 5%, then that spoilage event, if we can reduce that by 5%, we can save £3 million per year per line. Okay. If we can take an action to minimize the chance that the machine will fail, we're going to prevent those stoppages and help us reduce those spoilage events. So the way we're trying to do it is predict failures in advance, and then more importantly, give extra information about the failures. So is there any information that can help the operator diagnose the problem? Okay, so I'm going to speak a little bit about the actual manufacturing problem because it's quite complex. So this is a body maker machine. It's made up of two separate machines, a can maker and a head maker. But what we've set up is a set of sensors on the can maker. Now, as I've said, each body maker machine loads a single cup, and that single cup is taken at the beginning of a stroke and hit with a punch quite hard. So the mechanism looks a little bit like this. It's all a bit confusing, but the important bit that you need to be looking at is this device over on the right-hand side, which is the punch. And you can see the punch is a device that runs on a cam, and several times a second, this device pushes a cup through these tool devices to stretch it out from a cup of this height to a can height. Okay. And so you'll see here, this is the tool pack that I was talking about. We've got these ironing dies. They're 3 metal rings that will basically take that cup and thin it out and make it into the shape of a can. And you see the device at the end with the number 13 on it. That's what puts the little dome in the bottom of your Coca-Cola can. Okay. So during the cycle, during that circular motion where we're running through that punch, we can see various events that are occurring, events that where there is a chance where the metal making up that can tear and jam the machine, stopping production. So what we wanted to do was build a sensor array that we could retrofit on these body maker machines. So our partner built a tool pack that would fit on a sensor array which would fit onto a standard tool pack, and that's basically made up of a set of load cells and a set of eddy current cells. So the load cells pick up force that's happening, and the eddy current sensors are measuring distance. And the point behind this is, if we go back to that event cycle I was talking about, what we can do is use information from those sensors to actually detect times on that event cycle. So you can see the regions that I'm talking about here. You can see that in region number 1, that's actually when the RAM is going through the third ion that I was showing on a picture earlier. And then there's a section in the middle where we're checking the height of the can, and that's the traditional approach to finding whether a short can is happening. And then the section at the end, number 3, is the end of the punch, where it's pushed to the end and then starts recycling back. So, with these sensors, what we're hoping to do is detect when a problem occurs before one of these cycles happens. Right. Now, the problem is we've got an issue with the data that we're collecting from these devices. There are 7.5 billion IoT devices in the world. There's, as I'm sure you know, IoT data is abundant everywhere. And what happens is that the data is traditionally centralized. And what we've been trying to work out is that actually always bringing the data up into the cloud and then training your models and then sending those models down is not always, it has some problems. The data is complex and expensive to move, and you need a large infrastructure and engineering overhead. And also, there is a reliance on network connectivity, which, if you're in a factory situation, as we well know now, is that the connectivity in a factory isn't that reliable, because you don't have a nice Cat5 cable that you can plug in. You're having to use a network, a mobile network, and that can be easily disconnected. Also, we're actually working in partnership with a company that supplies their can making machines to 2 of the largest can manufacturers in the world. So what they want to do is make sure that the data from one can manufacturer is not used by the other can manufacturer. So data privacy is an issue. So many of you will have seen a diagram like this before, or understand the principle that actually the ML code in the middle, the bit that you guys are focusing on writing and worrying about, is actually a small part of the problem. And there's a lot of overhead all around this that we have to build. So that's a problem we had to overcome. I'm not going to spend too much time explaining it. But the main thrust of our idea was to, rather than always take the data all up into the cloud, the idea is to move the model closer to the data. So trying to get the model running at the edge. Now, the first step was just to get the model to run in an inference mode at the edge and make sure that the architecture would allow training of the model in the future. So, the idea of this decentralized approach is that rather than always training a model on everyone's data in the central cloud, the idea was that you could actually either train models on the data specific to that one use case, or in a decentralized pattern, perhaps just doing the training at the factory level and deploying the models. Our goal is to do fully federated learning, so that we actually have a mechanism where we can take the weights and biases for all the individual models and then average them out and create a new global model for deployment out onto all the devices. To achieve this, we had to build an architecture that would effectively run the same at the edge as in the cloud. And so The point we have reached now is that we have an architecture that runs in both areas, but what we've tried to do is break it down into the components that I showed you earlier and make sure that they can run in either at the edge, the ones that are highlighted in red, in the cloud, the ones that are highlighted in blue, or both. So you'll notice that there's a lot of those components that I was talking about. We're now in the situation where they will run in both areas. So we can deploy models out to the edge. We can monitor models running at the edge. At the moment, we're working on making sure that that training piece can be done at the edge. And to achieve that, we've built our Octopipe platform. We have a version of the Jupyter notebook, which we call Octilab. That has a series of templates within it where you can build machine learning models based on those templates. If you follow that pattern, then they will be easily deployable out. We have the Octa Store, which is effectively a repository of models that we have designed and trained against other data. You can take those models and either use them directly against a set of data, or you can train them against new data and then republish them as new models. We also have a conversational AI, which will allow us to troubleshoot issues, basically asking questions in a human way to get data out of the system. We also have a set of reporting tools, the Octadoc, which is a set of system health monitoring tools. So actually using Octopipe to effectively monitor Octopipe as it's running, so you can see how well the process is running at the edge. And then the real bit, the Octasite, which is showing you the dashboards that relate to your individual use case. So this is the platform that we started building out. Again, this is another view of the same idea, that at the edge we're doing all this data collection and model inference, and you'll see that some of the components that are running at the edge also run at the cloud, and we're mirroring the technology. So we're able to run all of these services either on-prem or in the cloud and move things between them. Again, the next set of pictures are just a drill down on this architecture. So I'm just going to scoot through them. If anyone has any questions, I can drill in at the end of the presentation. But we have an overall architecture built into the 4 components. The idea of the edge compute and the fact that we can collect data from the sensors, and then the data is captured in a local repository, which is then synced to the server. So the actual architecture running at the edge is identical to what's running up in the cloud. It's just running for that machine's data. And then the cloud compute and storage. Again, we're using more open source tools. We're using Kubeflow and Kubernetes to allow us to orchestrate the tasks, orchestrate the components that build up Octopipe, and orchestrate the jobs that make up a machine learning pipeline. Again, I will talk briefly about the types of models that we've been using. So one of the things that one of the most important things we've been doing in this use case is predicting future failures, so remaining useful life. And there's a couple of different basic approaches to doing that. Effectively saying, well, is there going to be a problem occurring in the next n time steps? And that's just a on-off, or alternatively calculating a percentage of that happening. And what that means is that gives us an idea of what is the chances of it happening in the next n minutes, or the next n minutes plus y. The idea being that if you're an operator, you want some kind of early warning system that identifies that, is this machine going to fail before that machine? So which is the one I need to focus on? Again, there are various different models, and I won't bore you with the details, but basically there are different types of models that we can use which will allow us to do better prediction, but some ones will actually give us more explainability. And the idea is that all of these models will still run in our pipeline platform in the same way. And the idea is that we can use some to make predictions and then some to help you explain why those predictions are going to happen. So it's going to fail in 2 minutes. It's because the coil of metal isn't correctly aligned. That would be because it's going to happen, and this is why. So again, we've been talking in the future about moving to doing online learning. This is something we're not doing at the moment. The model that we have for building the ML pipelines is the traditional approach. We break the data down, the historical data, into a train, validation, and test set. And then once we have a model that we are confident will work, it is deployed out onto the NUC device and it's made predictions. But the whole point of it is that when we're running the model in the cloud against historic data, we can decide whether it would have performed better than the model that is running at the edge and then deploy it out. And again, because we're using this same architecture, that means that we can push the deployment out easily. Now, what we've tried to do is break the concept of this machine learning pipeline down into easily reusable steps, and some of them we use in the training pipeline and some of them we use in the inference pipeline, but each component looks identical, so we can run one after the other. And here is an example. We have a process where we have some pre-processing of the data, that data cleaning step that needs to happen. Then you have a feature engineering step that takes the raw data and generates features. Then, depending upon which model is being used, if you're training it, you'll need to do some feature selection. But if you're running it in inference mode, those features will have to be available. And the idea is that this process, whether it's running in a training mode or an inference mode, these steps are identical. You just plug and play the ones you want to use. And what we have, as I've said, is this the Kubeflow mechanism for orchestrating those different steps in the pipeline. Okay, now I've mentioned that we're taking a very, at the moment all the data's coming back up into the cloud, but we have been doing experiments with federated learning and actually have some successful outcomes where we're predicting the capability of federated learning models against traditional machine learning models. We're yet to get anywhere near deploying that out into production, but it's a positive step. And we've talked about the fact that in this environment there is, I talked about the fact that when you're deploying a model, you need to look at whether the model is performing better than what it would be in the real life situation. And there's a few things that occur, especially in this use case, around the concept that the data coming in from the devices is going to change. The models are not going to be as effective as they were. So we need to make sure that we're constantly monitoring the performance of the platform and able to redeploy new versions of the models. Okay. Now here are some of the dashboards that we've been building. I mentioned the OctaSite and the OctaDoc. These are the kind of dashboards that we've been developing for customers. The idea behind monitoring the actual platform. So not the engineer who's looking after the device, but the engineer who's interested in how well the pipeline is working, can fix problems and understand information that's being captured. But also, the operator of the machine gets information about how the machine is performing. And as I say, the idea behind this architecture is that we can, our edge devices at the moment are actually reasonably high powered. We've had a fair bit of experience of deploying models onto relatively low power devices, but for this architecture to work, we've been using NUC devices, which are effectively like a laptop, a reasonable laptop spec running these models. But we've been focusing on trying to make sure that the inference model can run at the same time as potentially training later on. And the idea is that you can, again, because these components are very similar, you can scale them out on multiple devices. But the thing that we are really pleased about is because of that reusable ML pipeline, you can actually scale out to different use cases. And as I was saying earlier about the concept of you have one model that predicts something's going to happen, then another model which is actually looking for the underlying reasons as to why that thing is going to happen. And so we have a remaining useful life model, but we also have an anomaly detection model running at the same time against the same data, trying to detect what are the outliers that might be causing that remaining useful life. Okay, a whistle-stop tour. I'm not quite sure whether I've actually been talking for too long. I have a feeling that I probably have. But basically, at the end of it, at the end of this 18 months with a customer deploying our product to them, the idea is that we have delivered these things to the business. And I've gone through them, but I'm going to restate them now. We are able to predict tear-off events, and that has reduced downtime through stoppage. We're also able to analyze why those tear-offs are likely to happen, and which means that the operator has information to deal with it. Now, we're also able to do downtime forecasting, which allows a better maintenance planning. At the moment, what happens in these factories is they have a maintenance window and it happens whether it's needed or not. But the other thing that we've gained out of this is a lot of information about the physical process causing downtime. So we've had lots of problems with the actual sensors being in a unfriendly environment, being hit with hammers, cables getting caught in things, and it's understanding those kind of issues and a redesign of that tool pack that we talked about. Okay, from a technology point of view, which is the bit I'm really interested in, those pesky business people, I'm actually excited about the fact that the engineering time, we can reduce that because we have a standard package that we can deploy over and over again. And I keep saying we can reuse it for different kinds of use cases. And we've spent a lot of time optimizing the data transfer. Even though the end goal is to try and reduce that, we've had to spend a lot of time making sure that that data transfer can work over an unreliable network and it can work on a mobile SIM rather than having a nice big fat Cat5. We've built this MLOps monitoring platform, which allows us to detect when there are problems going to happen with our own tools. And as I said just a minute ago, we're actually reducing that reliance on network connectivity. Okay, I know it's the end of the day. Has anyone got any questions?